Hello.
Hello.
How you doing?
Oh, yes. Great to hear. Great to see you.
Yeah, nice to see you, Gregory.
Yeah.
So where are you physically?
Pescara, Italy.
Okay.
Yeah.
It's very early morning.
Oh, we're used to it during this meeting.
Yeah, we are in the very early afternoon.
Right. Okay, EFA, you are chairing this session. Let's start maybe. Are you online, EFA? We cannot hear you well. Hello?
Yeah, we can hear you very well, but don't hear EFA well.
Yes. Yes. There is probably some problem on his side. Let's see. Hello, EFA. We cannot hear you, and we cannot see you either. Makota, good day. Hello.
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 Can you hear me?
Yes, we can see you. We can hear you. Good. Wei Min, are you there? Hello, Wei Min. We cannot hear you well. Hello.
Women was online, yeah. Women was online a couple of minutes ago.
Yeah.
It's still online, but his video was turned off.
Okay. Well, if there is a problem with the EFA, maybe we can anyway start the session and he can in the meantime try to fix the problem. Good morning, good day, everyone. We are starting the last plenary session of this Maxwell Grossman meeting, 16th meeting, and it's a pleasure to introduce Shoan Nanjan, who will be our first speaker today. Nanjan, please, can you share your screen?
Okay, I will share my screen. If he just talk to me, he can hear very well, so there's no problem.
Okay.
Yeah, if he send me a short message, so that should be okay.
Okay.
Let me share. Okay. Good morning, good afternoon, and good evening, everyone. I first like to thank Professor Ruffini and the organizers for inviting me to give this presentation. I want to talk on the highlights of Insight-HXMT, as you know, China's first X-ray astronomy satellite. And also I will mention not much, a little bit on a future mission EXTP. There is also a dedicated plenary talk on EXTP, so I will not talk too much about it. First, I would just want to introduce to you on this screen. This is what we do in Institute of High Energy Physics in the Particle Astrophysics division. As you can see here, we are mostly working on a number of space missions, including the one I'm going to talk about, HXMT, and the next one, the EXTP, and a lot of other experiments, and also including one on space station and so on. And we also work on the on high altitude observatories, and for example, in Tibet, we call Yangbajing, YBJ, it's a cosmic ray observatory, and also in Sichuan province, Lasso, also the cosmic ray and the high energy gamma ray. And we are also working on, we call the ALI CPT, it's the microwave telescope aiming for detecting the B-mode polarization of in the microwave background in order to see the gravitational wave, the primordial gravitational wave. And we also work on the underground neutrino experiment. So it's just a quick overview of what we do in our laboratory. Now on Insight-HXMT, this is China's first X-ray astronomy satellite, was launched in 2017. The main feature that's summarized here, we have a large effective area above 30 keV, although we cover 1 to 250 keV, but above 30 keV, we have a very large effective area. I will show you. We have a good timing resolution because we record every single event detected. And currently, all instruments have been performing very well in orbit, and we have been focusing on bright X-ray sources, and this means mostly the transient sources. And we also carry out a lot of TOOs. We don't have much restriction for TOO except for the solar angle constraint. Otherwise, we can take TOO observations, not automatically, but manually. The turnaround time is typically hours to a couple of days. In addition to pre-approved TOOs, which usually have about 3 months preparatory data time, and we also do a lot of ad hoc TOOs. For the ad hoc TOOs, we reserve the DDT time quite a lot, and the data go to public immediately. We are currently near the end of AO3. AO4 will start in August, that is next month. And our guest observing program is open worldwide. In this round for AO4, we have received many proposals from Europe, from US, and from the rest of the world. And the program has been already approved and will start very soon. And according to the satellite status, the instrument working well, and the satellite itself is also working well. We still have a lot of redundancy, a lot of redundant resources. So therefore, we expect that the mission can last for more than 8 years. That is at least 4 more years. So here I show you the picture of the launch on the day, and also that's the artistic image of the satellite. Here I want to show you very briefly what we have on board. We don't have the conventional focusing telescope. Instead, we have traditional collimators, and in all the energy band. So starting from the low energy, we have a relatively large area of silicon. It's basically the fast readout CCD, covering 1 to 15 keV. Then in the medium energy band, we have also silicon. We use the pin diode. It covers about 1,000 square centimeters. Then we have the largest array of detectors, also with the collimators, covering the energy band 20 to 250 keV with effective area about 5,000 square centimeters. Here, just to show you, after taking into account all the responses of the instrument, we have the effective area from a couple keV all the way to 250 keV. As you can see, as the energy increases, we generally have a large effective area in order to cover the power law or even power law is cut off up to a couple hundred keV. That the instrument was designed to do this work. Here, since this is only a brief overview of the missions, I will not show you all the work. I will show you just a few highlights of what we have done. And we detected this 90 keV cyclotron feature from this Euclidean pulsar, which is also active very recently. And this 90 keV is the highest energy of the fundamental frequency of any of the electron cyclotron feature from any accreting neutron star. So therefore, this can be translated into the highest magnetic field directly measured. Of course, we know the magnetic field of magnetars must be higher than this, but those magnetic fields are not directly measured. So this translates to the directly measured highest energy, the strongest magnetic field. In comparison, before our detection, New Star and Suzaku together has detected about 80 keV. That should be the same line, but because the limitation energy band, that detected about 80 keV with about 4 sigma significance. With our data, one, because the source was very bright in our observation, and also because we have a very large effective area, about 100 keV, so we have more than 20 sigma detection. This allows us to study actually phase resolved cyclotron feature for this source, and also, of course, the continuous spectral features. And recently, there have been a couple more papers published from these observations, focusing on the change of the energy when as a function of the luminosity as the source evolved. Now, another very interesting thing, and I think a lot of people are aware of this historical event, this IFRB 20428. It was first reported by the Canadian radio telescope CHIMI, and very quickly by STARE 2 in the same event. And CHIMI detected the double pulses from this IFRB from the general direction of a neutron star in the Milky Way. And at the same time, actually 10 hours earlier, we started the TO observation to this because this magnetar was active a couple of days ago. So we started the TO observation. As you can see that after correcting for the same time, a very bright X-ray burst detected. And not only that, we also identified these double pulses of X-ray light curve in this high energy, medium energy, but not so much in low energy, very weak in low energy. We also studied the spectral evolution of the burst across the whole burst. As you can see, the spectra becomes harder when the two radio bursts were produced, and during the peak of the X-ray, the peak energy also reached the peak during the radio burst. And because we have the collimators there, we also have the capability to localize this X-ray burst. This is a comparison. These white contours are the localization from our instrument. Then this is from CHIMI, this is from STARE 2. And our location is perfectly in agreement with this magnetar, with off by only 3.7 arc-minutes, while over 1 sigma error is 10 arc-minutes. So therefore, positionally as well, this X-ray burst must come from this neutron star. So therefore, we identified this X-ray burst with this magnetar, and because the timing coincidence of the two pulses, so therefore this X-ray burst is also the same event of this radio burst. So therefore, we identified the whole thing from with this radio burst. And very recently, we have further analyzed our data, and we were able, as you can see here, to identify the two X-ray peaks more accurately and with more statistics, because we recovered more events from our data. And in comparison with the FRB, the two double pulses, that you can see they arrived almost the same time. But however, the duration or the separation of the two X-ray pulses is wider than the radial, than the two radial pulses, more than 6 sigma significance. We attributed this as due to the gravitational redshift of the X-ray signal, if they produce closer to the neutron star surface than the radial burst. So therefore, we can constrain the radius of the X-ray burst to be very close to the neutron star surface. And this paper has been submitted very recently. Because we have very large effective area, we were also able to detect the QPO signals from many black hole X-ray binaries. Here I show you one example. This is one extreme example that from this 1820, as you can see, we detected low frequency QPOs from low energy all the way above 200 keV. So this marks the highest energy of quasi-periodic oscillation from any neutron star. And because the energy is so high, and also because the lag between the high energy QPOs and the low energy QPOs is so large that it's nearly 1 second. So therefore, the traditional model, either radiative transfer or precessing corona, would not be able to explain this data naturally. And in order to explain the data, we developed a model of compact jet from the vicinity of the black hole. The main idea is that in this X-ray jet, this X-ray jet is curved, it is twisted, and the higher energy photons is produced near this, and lower energy photons are produced near the top of the jet. Then when the black hole rotates, it drags, the space dragging makes the jet precesses. And as the jet precesses, we see the higher energy photons coming from the base of the jet first, as shown you here, then lower energy photon, then even lower energy photon. So therefore, we can see the phase lag and also the coherence of the QPOs over this very broad energy band. So this is probably the closest X-ray jet to a black hole. And also for the same source, in another paper by studying the broadband energy spectra, we also have some interesting finding. As you see here in this paper, and this ratio between the spectral and the power law fitting, you can see that this ion line feature is very clear, and also reflection feature is also very clear. And from the ion line feature, as you can see, the width of the ion line does not change, although the narrow line component, the narrow component changes, but the width of the broad component doesn't change. This feature basically agrees, the ion line feature agrees what has been reported in Coron et al. In the Nature paper, where they concluded that the base of the corona does not change, but the height of the corona, that is, size of corona shrink during the X-ray outburst. But then because the size smaller, we should see more reflection from the disk because the corona getting closer and closer to the accretion disk. But however, that's not what we see. We see the reflection actually decreases as the outburst continues. Not the only story. So we studied this, and finally, we proposed that while the size of the corona indeed decreases during the outburst, but the plasma in the corona has a higher and higher velocity, outflowing velocity. So it's the special relativistic effect. When the velocity increases, which makes the reflection component becomes weaker. So the corona shrinks in the meantime. The corona itself is actually a jet. The jet velocity becomes higher and higher. This not only we can do pointed observation, we also can do monitoring, in particular for gamma burst. So therefore, we have a dedicated mode for gamma burst. In the regular mode, our anti-coincident detector system iodide can also detect the gamma burst in this energy band, 40 to 600 keV. But however, if we change the gain of the electronics, that is to lower the photomultipliers high voltage, then the energy range of the anti-coincident detector becomes 200 keV to 3 MeV. This energy band is adequate for studying the E-peak energy of gamma burst. And because of this, we have so far detected about 80 gamma bursts per year. Allows us, for example, to study E-peak of the gamma burst. This is a comparison of the effective area of HXMT in comparison with other instruments. Here we did not include the integrals because integral it has a large effective area, but it cannot measure energy spectra. So here we in MeV energy range, we have a large effective area and also good timing resolution. We record every single photons and we can measure the energy spectra quite well. With this, we detect about 80 gamma bursts per year. This shows you a couple of examples that if we combine our detectors, this from HXMT with the GBM, you can see in this energy range, that's where the E-peak energy is located. We can have a better constraint on the spectral parameters. Now, in the last couple of minutes, I'll go through the future mission because EXP enhanced X-ray timing and polarimetry mission. This we consider the next international flagship X-ray mission. Currently, we are planning to implement the mission, to launch the mission about 2027. This is basically a follow-up mission of HXMT by having a large effective area, better energy spectrum measurement, and in fact, we are also have a polarimetry measurement. And the main science will be focused on black hole, a neutron star, and also the physics and extreme gravity, magnetism, and density. So here I just show you very quickly that we have four arrays of instrument. The spectroscopy focusing array and the polarimetry focusing array will be led by China with the European contribution. And the larger area detector array and wide field monitor array will be led by Europe with some contribution from China. As you can see here, that in all these energy ranges, in all these instruments either have a very large effective area or in fact have a large stand radius. This 380 square centimeter is actually just a part of the instrument. Now we have even more for that. Here I want to go through the instrument very quickly. Will be a dedicated talk later. The mission hopefully will be launched by China Long March 7 or Long March 5 satellite. It's not finally decided yet. Long March 7 is a smaller launcher. Long March 5 is a larger launcher. It will be launched into a circular orbit with zero with equatorial orbit, and the total weight is 4.5 ton. We will have very high telemetry rate because it's a timing mission. We are going to record every single photon there, so we will transmit a huge amount of data. We will have alert system because the wide field monitor will detect a lot of transients on board. So this transient alert will be sent down both by China's Beidou navigation system and also by VHF transmitters, which is heritage from the SWAN mission. Okay? Now, a couple of examples for the science. This shows you just a simulation of matter moving around the black hole. And then these X-ray signals will form, of course.
What happens?
And if you make power density spectra, you can see here, you see some peaks, but not very strong. With EXTP, for the same kind of thing, we will see signal to noise ratio about 10 times better. Right? So therefore, we can study the strong gravity near black hole or neutron stars quite well. And for neutron stars, another important thing is so-called equation of state. It's with neutron star, we can study the low temperature and high density matter. There's no other way we can study. We can only do that with X-ray mission. And our goal is trying not only to measure the mass radius relationship for a couple of neutron stars, but in fact for a dozen of neutron stars very accurately. Because we have spectroscopy, timing, and also polarimetry. Hopefully all this together will allow much better determination of a dozen of neutron stars. Okay. For its spectroscopy focusing array, so here show you the instrument for the spectroscopy. We will have 9 telescopes. Okay, so each telescope has more than 5 meter focal length, and this will be mostly non-imaging with SDD, array of SDD with a very fast readout and a very good timing resolution. And in comparison with Athena, as you can see, above 2 keV, we have a larger effective area. Below 2 keV, Athena is a better instrument. For these lead detectors, we will have a very large array of these with effectively 3.4 meters, also with the silicon drift chambers, fast readout, good energy resolution, and so on. In comparison with other collimating instruments, for example, the RXTE or AstroSat, you can see our effective area will be much, much larger. Then on polarimetry, we will have 4 telescopes on polarimetry using essentially the same instrument of XP, but just a more advanced version of the polarization detector to be provided by the PISA group, the same group that provided the instrument. And in comparison, you can see here that this effective area of EXTP polarimetry and this XP, this CP, of course, is no longer there. So therefore, we'll have effective area many times larger than XP. So XP will open the window of X-ray polarimetry in the next few years. And then this will be followed by EXTP for much more detailed study. And finally, we see that the wide field monitor, it will be an array of them currently here, eventually maybe in different places. The main feature is that we will have a very large field of view, 3.2 standard radians, covers this very important energy band for X-ray transient, 2 to 50 keV. Essentially covers both thermal and non-thermal signals. And also for gamma ray burst with very high redshift gamma ray burst should also fall into this energy range. And we will also have adequate energy resolution. A very powerful instrument. In terms of the field of view, you can see an instantaneous field of view of the wide field monitor is very high compared to any other OSCAP monitor previously or currently in orbit. So therefore, this instrument will provide triggers of many transient events and monitor essentially all the galactic transient sources over the mission. Right. So finally, just want to show you with this special way. That is, I did the ADS search on HXMT and EXTP. Here, I just list the statistic on ADS citation to HXMT and EXTP. As you can see here, it increases very rapidly for both missions. So this means HXMT is starting to have an impact in the community, and EXTP is very much welcomed by the community. So we look forward to have to continue HXMT and to launch EXTP in the near future. Thank you very much. I'll stop here.
Thanks, Sean, thanks for your nice talk. Can you hear me?
Yeah, very well.
Okay, it works.
Nanzang, let me congratulate immensely from not only for this beautiful presentation, but for seeing for the first time the physics and astrophysics that we were waiting for since 50 years. Finally, finally, we have seen in the theory the machine which can generate the energy extraction from the black hole. But now we have seen a new result that you can follow this energy extraction and the difference spectra as it goes away from the black hole. But even more, that you can start to see the interaction of the disk with the black hole. This is fantastically beautiful. And of course, the fact that you are still expanding from HXMT to EXTP, which is strong amplification of the instrument, and with also Italian collaboration with Feroci, make us look at the future with a lot of optimism and interest. Congratulations again.
Thank you very much, Remo. Remo, I want to report to you one more thing, which I forgot to mention. The ESA, Italian Space Agency, is considering to set up a mirror site on HXMT's database. So very soon that the European scientists can download the data directly in Europe. They don't have to go through the Chinese network. So very soon that will be happening.
This is very important.
To Chinese National Space Agency on this. Thank you.
And this is very important. And it's also important that the chairman of the session is EFA, because we are preparing between ICRANET and the University of Science and Technology of China a PhD program specially designed to prepare graduate students both in China, all over the world, and in ICRANET. Therefore, it's very, very significant that this last session be chaired by EFA, who is the leading force in the USTC.
Yeah, thanks to Roma's support, we can do some collaboration on education. Sean can do more on science, I think.
Yes.
Yeah. Okay, so if there are no question, I have a short question to Sean. Do you think magnet is the best model for shorter fast radio burst?
Certainly that we see that for this one event, we see the radio and X-ray signal simultaneously, but only one. We see many more X-ray events, actually flares actually burst from magnetars, but only one radio event. So this is still not known yet why these magnetars that produce X-ray events so frequently, but not very frequently on bright radio. But they produce faint radio signal. Okay, that's very faint. As a fast telescope has seen many faint radio burst from magnetar, but not many bright ones. So either this is because of beaming effect, or it's just the magnetars are just part of a story. So we don't know. So until I believe we can see one magnetar in other galaxies with X-ray and radio event, then we will know the story much better. And also, this is the thing I want to report to Remo, that we are collaborating with Ferrara University and also other Italian colleagues on doing simultaneous observations in radio, optical, and X-ray on many FRBs. So far, we haven't seen the simultaneous extragalactic FRBs with X-ray, but we have placed the interesting upper limit. So we are waiting for the one groundbreaking event simultaneous in radio X-ray. So that will tell us a very good story. Thank you.
Thanks. We are looking forward to see new discoveries from HXMT and also FAST. Okay, thanks, Sona.
Thank you.
Thank you.
Yeah, our next speaker is Weiming Yuan. He's from National Astronomical Observatory of China. He will talk about another X-ray satellite, Einstein Probe mission. Weiming, are you ready?
Can you see me?
Yes.
Okay. Can you see my screen sharing?
Yes, perfect.
Okay. Okay, good morning, good afternoon, good evening, everyone. I would like to thank the organizers to invite me to present the Einstein Probe mission. It's a privilege and a pleasure to attend this exciting conference. So Einstein Probe is a future mission of the Chinese Academy of Sciences in collaboration with ESA and MPE in Germany. So in this talk, I'm going to give a short introduction to the science drivers and the design concept of the mission and the current status and a few science prospects. Okay, let me start with the current and the future X-ray wide field monitors in X-rays. There are currently two operating all-sky monitor missions in orbits. MAXI, which is on the International Space Station, which is a JAXA mission working in 2 to 30 kV band. It scans the whole sky once every orbit, which is 90 minutes. And the SWIFT, it's a well-known mission of NASA. It's doing the gamma burst science, but it also monitor a large part of the sky in a hot X band. And in next year, the China-French joint gamma burst mission SWARM will be launched. As you can see that all these current and future X-ray monitor missions make use of non-focusing instruments. For example, the pinhole oscillator camera or the coated mask technology, which limit the detecting sensitivity as well as the spatial resolution of the X-ray detection, although the field of views are very large. Okay, so in recent years, there have been some very interesting new types of high-energy transients being discovered. Namely, for example, the black hole tidal disruption events. They can tell us about the demography of black holes in the universe and how matters fall onto black holes and how jets are formed. High redshift GRBs, they can answer the question of when the first stars in the universe formed and how metal enrichment in the universe happens, and also reionization of the early universe. And the supernova shock breakouts are very interesting objects telling us about the supernova physics and also the progenitor stars. Electromagnetic wave counterparts of gravitational wave events are no need to say that these events are very, very hot topic these days. And we can learn about what are the EM counterparts of these events and how compact objects merge. And the EM counterparts of neutrino events are also very interesting objects, and they can tell us about how the high energy particles are accelerated. And very recently, the very intriguing objects, which are termed as the quasi-periodical eruptions in X-rays, they might be related to extreme mass ratio in spirals as gravitational wave sources. These are very interesting types of new transients. However, are detected only in very small numbers. Okay, a few or even one for EM counterparts of GW sources. So we definitely need the next generation of X-ray monitors to see both deeper and further, and also at high cadence. So this is how the Einstein Probe mission was proposed, and I demonstrated here the basic science requirements for the next generation of X-ray monitors. What I plotted here is the limiting magnitude and versus the energy band for the current and the future X-ray monitors. As you can see, Fermi and GBM, GCAM, Maxi, SUID bad and SVORM. And so we in order to detect more the interesting new types of transients, we really need to go to higher sensitivity by at least one or even more orders of magnitude than those currently in orbits. At the same time, we also need a very large field of view. So ideally, it should be a load less than 1 steradian, the field of view. And also from this diagram, you can see that most of the present and future X-ray monitors are working in the hard X band and soft gamma ray band. And in fact, the soft X-ray band has been poorly explored in terms of the time domain size. But the question is, how can we do this? How can we increase the detecting sensitivity in the X-ray band by more than 1 order of magnitude? The answer is very simple. So we should go to X-ray focusing imaging, okay? Because all the past and the current, the future mission, some of future missions were using the non-focusing imaging. So we should really go for focusing imaging in X-ray. So fortunately, there is a new technology to do this. This is a so-called Lobster-eye micro-pore optics, or MPO, for X-ray focusing imaging. So because I have no time to explain in details how this works, but very briefly, so the MPO, or micro-pore optics, is simply a curved microchannel plate, curved in a spherical shape. On this plate, there are many small square holes or pores, they call it pores, and each of these pores is pointed towards the curvature center of the sphere. Okay, so when an X-ray source is seen, the incoming X-ray photons can be reflected on the walls of these small pores. And by the grazing instance reflection, which is required for X-ray focusing, the X-ray photons can be brought onto the focal, the so-called focal surface. It's not focal plate, it's focal surface because it's also a spherical shaped focal surface. And as you can see that certain optics has no major optical optical axis. So every direction is equal. So which means that for any sources coming from any direction, they will have the same imaging principle, and there is even no vignetting effect. So in this way, we can build such micro-pore optics into a very large field of view. If you like, you can build into a monitor of the 4 pi solid angle. Actually, this was first proposed by Roger Angel in 1979, and following up that, it has been studied by a number of groups for many years. And also our lab at OC also started to develop this technology since 2010. The principle is actually exactly the same for the imaging principle of the eyes of lobster. Okay, actually, the idea was motivated by our understanding of how the eyes of lobster works. So that's why it is called the Lobster-eye micro-pore optics. So it turns out to be that such optics is an ideal optics for X-ray wide field monitor. It can give a very wide field of view and give a better angular resolution. The current resolution we can achieve is around 5 arc-minute or even better. So since we have a much better angular resolution compared to the non-focusing instruments, and we can get a much better detecting sensitivity because of the focusing imaging. And such a device is optimized for the detection in a soft X-ray band. On the right-hand side, I show you an X-ray image of a point-like source. And this is the X-ray image obtained at our lab at an AOC. And the full width at half maximum is 4.5 arc-minute PSF. The central point is the focal spot when X-ray photon is reflected twice on 2 adjacent perpendicular walls of the poles. If there is only one reflection, then it forms one of the cruci arms. So you can see the PSF is a central spot, bright spot, plus 2 cruciform arms. Okay, so this is the technology we are using to develop the Einstein Probe mission. So the Einstein Probe mission is the second X-ray satellite of the CAS following the HXMT Sean just talked about. The main science goal is to do the X-ray all-sky monitoring to discover and characterize high energy transients, and also to monitor the variability of known X-ray sources. So we hope it can work at a sensitivity at least 1 order of magnitude better than the current instruments in orbit. And so a very short account of the history of the mission. So we first worked on a concept of an X-ray all-sky monitor to be placed on the Chinese space station, and then later on we adopted to a free-flying satellite, the Einstein Probe, and we put forward the proposal in 2012. The adoption was in the end of 2017. Now we are in phase C, which is the performance validation phase. The official planned launch date is the end of next year, but that may be a delay of a few months, which is currently still under decision. The nominal lifetime is for 3 years with a goal of 5 years. As I mentioned, EP is an international collaboration among the CAS, the ESA, and MPE. So the main science objectives, we icon them into three items. The main science objective is to do a systematic survey of soft X-ray transients and the variability of X-ray sources at an unprecedented combination of high sensitivity and cadence. And we will discover many types of transients, I believe, and among them, we identify 2 types which we are mostly interested. The first is to discover otherwise quiescent black holes at almost all astrophysical mass scales, and other compact objects by capturing the transient X-ray flares. In terms of massive or supermassive black holes, they are tidal disruption events. The third one is to detect and localize the electromagnetic wave sources of gravitational wave events by synergy with gravitational wave detectors. Because black holes and gravitational wave are the two main prediction of the general theory of relativity of Einstein. We named the mission after this great scientist. So in addition to the main science objects, there are various classes of high energy transients that can be potential targets of the Einstein Probe mission. For example, the high-red GRBs and supernova shock breakouts, magnetars, and related the faster radio burst, and stellar flares, and the thermonuclear burst from neutron stars, and black hole X-ray binaries in our galaxies and nearby galaxies, and the intermediate mass black holes and the UAX, AGNs, of course. And also, we are very interested in detecting this quasi-periodical eruptions in X-rays, and also X-ray flares associated with multi-messenger events like neutrino events, and so on. So here is the design of the mission. The instrument, we have two main instruments. The first is the wide field X-ray telescope, WXT. Okay, so this is the instrument making use of the Lobster-eye micro-pore optics I just mentioned. There are 12 modules. So each module has a field of view of about 300 square degree. So in total, the total field of view will be 3,600 square degree, which is about 1.1 steradian. It's working in the passband of 0.5 to 4 keV band with a spatial resolution of 5 arcminute. The sensitivity we hope can reach 10 times or even better, better than the current instrument in orbit. And the next is follow-up X-ray telescope, because when transients are discovered by WXT, it is not enough. We should do deep X-ray follow-up observations to obtain the X-ray spectrum and the light curves to characterize them. So there are two units of this follow-up X-ray telescope. They are just common water-worn optics telescopes with narrow field of view, about 1 degree. It's working in the normal X-ray band from 0.3 to the keV band. The effective area of each of the unit is about the 300 square centimeter at 1 keV, with a very good spatial resolution of 30 arc seconds HPD on X-rays. And WXT is an instrument developed mainly by the CAS, and the FST are a joint effort of the CAS and the ESA and MPE. The spacecraft is being developed at the CAS Institute. We can do onboard data processing. So once a transient is detected on board, the spacecraft will be slewed and point the FST automatically to the targets to do automatic follow-up observations. Here is a design and also the product of WXT. So for each of the module, there are 36 MPO plates, and on the focal surface there are 4 back illuminated CMOS detectors, each of 6 centimeter by 6 centimeter. So they are all developed at the CAS Institute, and ESA is contributing to the test of the components and also some of the modules. So the technology challenges are huge, actually. This is going to be the first large field of view MPO telescopes ever built. The total MPO we're going to use is 432 plates. And also the detector plane is huge. So we need, essentially, we need 48 CMOS detectors to cover the whole focal surface. And also it's the first time to use CMOS detectors as an X-ray detector in space. Here I show the effective area of WXT. And this diagram shows the FXT field of view. You can have a sense of how large it is. It's 3,600 square degree. And on the right-hand side is the grasp parameter, which is the product of effective area with the field of view. So you can, in a comparison with some of the X-ray focusing instruments, as you can see that EP WXT has the largest grasp parameters. So for FST, we have 2 units, and they are the usual 1-to-1 type X-ray telescope, and the ESA and the MPE contributes to each of the mirror assembly, and also to MPE also contributes to the CCD detector modules, and IHAP is responsible for the overall development of these telescopes and also the building of the CCD camera. And I show here is the effective area for one unit of FST. So it has more than 300 square centimeter effective area at 1 keV. So the status. So we have built 2 qualification modules of complete modules of WXT, and 3 qualification modules of mirror modules. And on the left-hand side, you can see the QM1 of WXT module. This is a complete module with the optics and with the detector. Camera is just being under tested at IHAP last week, and the CMOS detector array and the WXT QM under thermal balancing test. And last month, we had our WXT MA, a mirror assembly module QM3, tested at Penta at MPE. And the testing results are satisfactory. This shows the X-ray image of point-like source, which can give full width maximum PSF about 4 to 5.5 arc-minute. And the lower left image shows this PSF, the image of the complete WXT module, combining the mirror, the focusing mirror, and the CMOS detectors. And here in the middle, I show you the testing results at the Penta at the MPE, which shows a quarter of the total field of view of one WXT module. Okay, so this is only 9 degree by 9 degree, roughly about 100 square degree. So you can see that there are 11 by 11 images which taken at different instance direction. So you can see that across the almost 100 square degree field of view, the imaging quality is almost the same, unchanged. So this demonstrates the very good large field of view performance of WXT. On the right-hand side, I show the measured effective area versus energy, and the measured data match the model prediction quite well. FST is being developed at IHAP, and I show here the first slide of STM module of the mirror module developed from ESA, and the tester was done at IHAP, and also the X-ray spectrum developed obtained by the camera built at IHAP. So the mission profile, so EP will be put on a lower circular orbit at 600 km with a low inclination angle of 29. So there will be an alert data rapid downlink capability by Beidou system of China and also VHF system of France. So we can very quickly downlink the transient alert information to the ground, to the science center, and then we release them immediately to the public community. So, and there is also a capability to send the TOO, target of opportunity, command uplink within 1 day, or for time critical events, perhaps within 10 minutes. there will be three operation modes. One is the survey mode by diversity, and autonomous actually follow-up observation mode by FST, and also target of opportunity observations. Here shows the all-sky survey mode. So there will be 3 snapshots per orbit, each lasting about 20 minutes. So in this way, in 3 orbits, which is 5 hours, we can cover the whole night sky. So we always point to the anti-sun direction. So in one day, there will be 45 snapshots, and many of the sky positions will be covered several times per day. And next slide shows the simulation of a one-day survey with WXT. And you can see this is one pointing, another pointing, the second, the third pointing. So in one day, there will be 45 pointings, which can cover the most of the night sky several times. So in half a year, we can cover the whole sky in half a year. And the next slide shows the stimulated all-sky image, including transients in 1 year data taking. So you can see in 1 year, we can detect more than several 10,000 X-ray sources, and also transients, GRBs, short GRBs, and the supernova breakout. And on the right-hand side, the lower part, right-hand side, I can show the monitoring of the LMC. So you can see we can have a daily monitoring of the X-ray sources for LMC. And how much time do I still have?
Yeah, you can have 3 minutes, I think.
Okay, good. Okay, so the EP is collaboration among Chinese Academy of Sciences and European Space Agency. So ESA joined EP project as a mission of opportunity, and also Max Planck Institute for Extraterrestrial Physics in Germany. And currently we are discussing with CNES, France, to make use of the VHF network and to set up a new potential collaboration with CNES. So let me conclude my presentation. I hope I can convince you that the X-ray sky is rich in various classes of transients and variables, and the future of monitoring the dynamic X-ray universe is very promising. This is enabled by the novel Lobster-eye MPO technology. And the CAST Einstein Probe mission will discover and characterize a large number of faint X-ray transients and monitor X-ray sources, the variability of X-ray sources. And I should mention that the follow-up observations by ground and the space-based facilities are essential. And the synergy with other multi-wavelengths and the multi-messenger facilities can offer great science opportunities. Here is the website of our mission. And I will stop here and thank you for your attention. I'll take questions.
Yeah, thank Wei-Min for your nice talk. So,
yes, Wei-Min, really impressive and very, and very. We are very few years from the seeing everything in operation, and this lobster-eye dream is really becoming a reality in this wide field, and therefore is part of this new flotilla of multi-messenger, which are really very impressive. We all look forward to this great result.
Yeah, is there any further questions? I think Wei-Min talk is
Thank you again.
Thanks.
Thank you. So I will stop sharing then.
Yeah.
Thank you. Thank you for your invitation, and bye-bye.
Thanks again. So our next speaker is Makoto Tashiro. He talk about the X-ray imaging and the spectroscopy mission.
Thank you for your introduction. I will share my screen.
Okay.
Can you see the screen?
Yes, perfect.
Okay. Thank you for your invitation and giving us the opportunity to introduce our mission, the X-ray imaging spectroscopy mission. This mission is formally called XARM, X-ray Astronomy Recovery Mission. So we reported some papers on this mission. The first one is the concept of the XARM, Astronomy Recovery Mission. And recently we published the status of CRISM mission as a SBIA proceedings. Also, the scientific objectives reviewed by the white paper of the CRISM, which is archived on as the Science with the X-CRISM last year. So please refer to these papers if you would like to know more in detail. Okay, today's talk, the contents of today's talk is around something like this. I will summarize the overview of the CRISM mission, and I would like to introduce some of the science cases that CRISM will do. And then I introduce the mission status and observation plan with this mission. The first one is the overview of the CRISM. The CRISM, X-ray imaging the spectroscopy mission, is a recovery mission of asteroid Hitomi. Hitomi was launched on February 17th, 2016, 5 years ago. It was a beautiful launch, and the bus and mission instruments were activated very well, and Hitomi started observations. However, due to a series of mishaps of the attitude control system of the satellite, Hitomi was broken up in the orbit on March 26th of this year. So the observation period was very short, only 1 month, but the results were impressive from my point of view. Since the observation was terminated before opening the gate valve. The gate valve is the protect window which protecting the sensor from atmosphere. Because of the gate valve closed, the bandpass is limited above 2 kV. Even with the limitation, the X-ray microcalorimeter installed on the Hitomi showed an unprecedented resolution as expected. And it enabled us to measure the turbulence velocity and detect very weak lines with only 300 kilosecond exposure in the space. This spectrum is the highlight obtained from Perseus cluster of galaxies. I believe this spectrum moved many persons and pushed us to resume the mission with CRISM. The X-ray spectroscopy provides us various information of astrophysics. The spectral feature of element lines is, for example, and absorption features in the X-ray spectra tells us the radiation mechanism and the temperature of the plasma and chemical abundance of the plasma. And measuring the lines, we can see the cosmological or gravitational redshifts. Line plotting tells us the velocity dispersion of the plasma. And of course, the line detailed feature review the ionization state of the plasma, which tells us the state of the physical state of the plasma. So the key device to realize the high resolution spectroscopy, which CRISM use, is the X-ray microcalorimeter. The X-ray microcalorimeter is a device measuring phonons, not photons, but phonons excited by penetrated X-ray photons. The X-ray photon hits the mercury telluride absorber by a few millikelvin. And the temperature rise is measured by the silicon thermometer attached below the absorber, photon absorber, with the accuracy of the microkelvin. All the detector should be cooled down to 50 millikelvin to reduce heat capacity and the thermal noises. For this purpose, to realize the extremely low temperature, we utilized the ADR and liquid helium installed in the vacuum cells called dual. The dual thermal shields are cooled by mechanical coolers, Joule-Thomson coolers, and two-stage Stirling coolers. The detector system is equipped on the focal plane of the X-ray mirror assembly. The 6x6 pixelized detector of the microcalorimeter with the X-ray mirror realized unlimited image capability, as well as the unprecedented energy resolution. The detector assembly and ADR are developed by NASA Goddard Space Flight Center, while the cooling system is developed by JAXA and Sumitomo Heavy Industry of Japan. Another instrument is the wide field X-ray CCD imager. We call it Extend. Extend covers the same energy band with the 200 micrometers thick back illuminated CCDs. The CCD is produced by Hamamatsu Photonics, is calibrated by the Extend team of Accretion team, and is installed in camera body with electronics by Mitsubishi Heavy Industry. The X-ray mirror assemblies for the Extend and also for the Resolve is the X-ray microcalorimeter system, developed and fabricated and calibrated by NASA Goddard Space Flight Center also. The X-ray mirror assembly is an aluminum foil X-ray mirror, utilized the epoxy reproduction replication method. So the basic strategy of this recovery mission is as follows. The main concept is to maximize the X-ray microcalorimeter science, since it is completely new science field that Hitomi opened and will not be done before the Athena era. So to strengthen this science, we choose a kind of conservative combination with the X-ray CCD camera. This is the brief summary table of required specification of the instruments of Crison. The 6x6 pixelized X-ray microcalorimeter with an X-ray mirror assembly called Resolve is emphasized with the high energy resolution of 7 eV at the 6 kilo electron volt band. This allows us to measure the velocity dispersion of ion line in the accuracy of 100 kilometers per second. The energy range covers from oxygen lines to highly ionized ions. A wider field of view of the CCD camera, covering almost the same energy band as we saw in the last slide. The spacecraft is 2.3 tons, which is 7.9 meter long, 9.2 meter wide, and the diameter of the base plate is about 3 meters. It is designed to work for the 3 years with cryogen, but after the 3 years with the cryogen, we can conduct a cryogen-free operation with the installed mechanical coolers. So the nominal mission period is 3 years, and we hope to continue the observation after 3 years. The orbit parameters are the same as those of Hitomi. The altitude is 575 kilometers, and the inclination is 31 degrees. The weak line detection capability of resolve exceeds the doors of Newton or Chandra above 0.8 kV. Especially for ion K-band, the performance is outstanding until Athena comes. The extent is excellent in Grasp capability, which is a production of effective area and solid angle, as you know. With the combination with the narrow field of view resolve, extent is useful to produce reliable science output from the brand new X-ray microcalorimeter system. This is the overview of the CRISM. Next, I'd like to introduce some cases of science studies. The scientific objectives as follows. Following Hitomi, CRISM will challenge to the question, how does the large structure of cluster of galaxies formed? We focused on the turbulence, pressure, of course. This shall be measured, as well as the gas pressure, thermal pressure, to reveal the dark matter mass and distribution in various stages of clusters of galaxies. And how was the element and energy produced and distributed in the universe? CRISM will reveal the metallicity of rare metals in supernova remnants and their expanding velocity in the interstellar space. And observation of accretion disk torus or disk of the compact objects, including supermassive black holes, will reveal the geometry of the accretion system. Also, observing the outflows from the disk winds or from the galaxy winds allows us to understand energy cycle with the material cycle in the universe. And I would like to emphasize that CRISM will lead us to unexpected new astrophysics with an unprecedented resolution in energy. Let me introduce some topics of science which CRISM will tackle. First one is the first science object that we saw in the previous chart, the precision. The precision of cluster cosmology depends on the accuracy of mass measurements. One of the most important ways to measure the cluster mass, which is based on the assumption of the thermal pressure alone supports the hot gas against the cluster gravity, meaning the hydrostatic equilibrium. However, numerical simulations show that the macroscopic motion, like turbulence of the gas, may provide significant non-thermal pressure support against the gravity. It could be up to 25 or 30% in the cluster of galaxies. In fact, Hitomi observed the Perseus cluster core, which is dominated by the central massive galaxy NGC 1275, and measured the line spread, line broadening. By measuring the line Doppler broadening, Hitomi SXS, this is the microcalorimeter on board Hitomi, succeeded to show that the turbulence velocity dispersion is 164 plus or minus 10 kilometers per second. This kinetic pressure is less than 10% of the thermal pressure on the scale of 60 kilo per second. CRISM will continue the Hitomi's legacy by measuring the velocity of gas motion and non-thermal pressure contribution with the accuracy of a few percent in many relaxed bright galaxy of clusters. The next. The second one is that I introduced is about the AGN feedback. XRISM will conduct the spatially and spectrally investigation on the AGN feedback. This figure shows the Chandra X-ray image with the VLA radio image of the core region of the Virgo cluster, which is dominated by the central galaxy M87. The image highlights the complexity of the structure in the gas. In particular, we note that the 1 kV gas indicated a lifted up gas produced by the AGN feedback. These structures are moderately resolved, should be resolved by XRISM resolve utilizing the imaging spectroscopy capability of XRISM. Each white box you see in the left 6 by 6 pixels shows the field of view of the results. By mapping with these field of views, XRISM will investigate the uplifted gas structure and surrounding ICM. Thus, we will resolve the uplifted gas in spectroscopy. This right figure shows the simulated 100 kilosecond resolved spectrum of one of the regions which we expect to observe the outflow in M87. The spectrum clearly shows the contribution from the different thermal components, meaning components with the ion airline complexes. This also allows us to distinguish uplifted cool gas from the ambient hot intracluster medium of 2 kV. Of course, the chemical makeup of the universe represents the sum of the billions of past supernovae in the cluster. Resolve will measure the abundance of the elements. With sufficiently long exposures, if we have, resolve will detect weak lines from rare elements in the intracluster medium, such as sodium, aluminum, chromium, and manganese. Aluminum and sodium are sensitive tracer of the metallicity of the underlying stellar populations, while chromium and manganese can be used to probe the characteristics of the supernova 1A progenitors. This results resulting in information about the chemical enrichment history in the cluster of galaxies. Next, the third topic is about the gravitational redshift around the relatively compact objects. XRISM will revolutionize how we understand accreting system in the supermassive black holes, starting from the hard-core gas flows from the interstellar medium of the galaxy down to the inner accretion flow, where matter is affected by the strong gravity of the black hole, central black hole. In 1995, Japan's ASCA satellite opened a new window in X-ray astronomy with the discovery of the broadened ion K lines in an AGN MGC-6, 30, and 15. The implication of the broadened line is immense, as it may provide a way of measuring the elusive fundamental parameter of black hole-like spins. As such, the broad ion line has ignited debate and continued interest for now. Rapid time variation is also observed by following observations. X-ray reverberation mapping and quasar micro lensing indicates that the broad ion K line is produced by reprocessing of the inner accretion disk within 10 RG. But the detail of the inner disk radius and the kinematics of the outflow of the flow of the still highly debates. By disentangling contribution from the other spectral features, narrow emission from outer disk and torus, or absorption through the ionized outflow along the line of sight, we probe progenitors of the inner accretion flow to make clean estimation of the black hole spin. QUISM can do. QUISM will give us a clear understanding of how much material is actually making the black hole and how much material is being removed through the massive outflows by distinguishing the narrow line outflows from the innermost broadened ion lines. The left chart, ion K line profile observed from the MCC6, as seen in the 300 kilosecond by XMM Newton PN, which is indicated in blue line, and Chandra HETGS green, along with the result simulated in red. The red QUISM spectrum alone shows the clear spectral features in this ion K energy band. This middle chart shows the ratio of the XMM PN spectrum to power law model between the 2 and 4 kV and 7.5 and 10 kV. The PN spectrum can be equally well described by pure relativistic reflection with an inclination of 5 degrees, or by relativistic reflection with the inclination 75 degrees with additional emission and absorption, including the ultra-fast outflow of 0.13 light speed. So this blue and red residuals, we cannot distinguish these two models with this resolution of the Newton. However, this chart shows the QUISM simulated spectrum. We see the QUISM will easily distinguish between these two scenarios with outflows, without outflows, as the narrow emission and absorption features in the spectrum. Next. Lastly, I would demonstrate our capability of direct observational determination of white dwarf mass. If we can measure the gravitational redshift of the spectral feature from the white dwarf surface, this can all change. We believe there is a strong possibility that we can do so by using the QUISM resolve X-ray microcalorimeter by measuring the 6.4 kV line, ion line, precisely. Right figure shows the expected degree of gravitational redshift. For white dwarf mass above 1.1 solar mass, the redshift will be larger than 2 electron volts, which is easily within the reach of the resolve resolution. Moreover, the gravitational redshift of the sensitive proxy of the white dwarf mass just below the channel cycle limit, precisely where the mass determination can have the significant impact. One of the symbiotic stars detected by BAT on SWIFT, the T Coronae Borealis, which is also the recurrent nova. Both this fact that the hard BAT spectrum indicated that its white dwarf is exceptionally massive, perhaps around 1.35 solar masses. That is the estimated mass. T Coronae Borealis exhibits a strong 6.4 kV line, partly from the reflection of the white dwarf surface. Therefore, T Coronae Borealis is an ideal target to investigate the mass and the radius by measuring the gravitational redshift from the surface. This simulated spectrum is guided using the 46 kilosecond Suzaku observation of this target, which is obtained in 2006. The CCD camera on Suzaku XIS data were well reproduced with the model absorbed by the partially covering observer with a single narrow Gaussian at 6.396 kV. If it is true, the inset shows that the Crescent resolve has a statistically qualified necessary to detect the expected gravitational redshift of this 6.4 kV line with the accuracy of 4 electron volt. This is well within the capability of the resolve system. Okay, let's move to the mission status. All of the instruments produced in various places of the world, they are all now gathering in the gathering in the JAXA Tsukuba Space Center, which is placed in the Tsukuba city in Japan. So something like this, the CCD system, CCD chips are now in fabrication in Mitsubishi Heavy Industry factory, and resolve system, which is produced in NASA sensor system is produced in NASA Goddard Space Flight Center and installed in the dual system in Sumitomo Heavy Industry in Nihama in Japan. Then it will be transported to the Tsukuba Center, Space Center very soon. And the XMA, the mirror system, is also produced and calibrated in the Goddard Space Flight Center and will be delivered in January of next year to the Tsukuba Space Center. The spacecraft bus system is now under transportation from the NEC factory to the Tsukuba Center by components. This is the summary of the status. The calorimeter sensor insert was delivered and installed in the Duo in Nihama, Japan, and will be delivered to Tsukuba Space Center next week. And it is dedicated for the subsystem integration and tests in Tsukuba Space Center. The mirror system will be delivered to Japan in January. The CCD chips were screened in Osaka University and is under assembly in MHI, Mitsubishi Heavy Industry in Aichi, Japan. The important milestones are these. The satellite integration will start in this summer in Tsukuba. The mission instruments will be installed on the satellite in the first half of the next year. Then we will have the proto flight test from summer of next year, and Crescent will moved to the Tanegashima and to be launched in Japanese fiscal year 2022, maybe in early 2023 of calendar year from Tanegashima Space Center. Last item is the observation plan. In the beginning of the nominal observation, in the beginning of the nominal observation phase, we conduct the performance verification observations. The initial observation phase is defined with 3 months after the launch. 1 week calibration, critical observation to activate the satellite, and we will have the commissioning phase for about 3 months. Then we move to the nominal observation. In the beginning of the nominal observation phase, we conduct the performance verification observation. This is planned not only to performance verification, but also to show the capability to the astrophysics community of the world. The PV observation target list is recently released on this site. So please visit this site. The CRISM science team consisting of the contributors of the development of the CRISM. Unlike Hitomi, the PV observation is conducted by the science team, but unlike Hitomi, CRISM introduced the CRISM guest scientist program to the PV phase observation. In order to enhance the science in the PV observation phases, a limited number of external scientists outside of the CRISM science team will be added to the original CRISM team. The CRISM guest scientists will be called and selected by 3 agencies, by JAXA, NASA, and ESA independently in the next year. After the commissioning, calibration, and the performance and verification, the guest observation will start maybe at the 10 months after the launch. Although the detail is not determined and not released yet, but the baseline is as we did for the ASCA or Suzaku with the Japanese X-ray astronomy satellites. Please wait for the announcement of opportunity, which will be submitted, released at the end of the commissioning or after the launch. So the approved mission term is, nominal term is 3 years. After the 3 years, we are going to have the mission completion review. If it is successful, we can continue the latter phase observation with the mechanical coolers. Okay, this is the view of the observation plan. Okay, I will stop my talk at this. The CRISM starts the scientific observation in 2 years. So these institutes are the contributor to the CRISM project. Thank you very much.
Thank you.
Thank you so much for these nice talks. Any questions?
Yes, I have a very short question. So the CCD is superconductor transition edge sensors or something else?
Sorry? So
I mean, what's the CCD you used? Is it a superconductor transition edge sensor?
Superconductor edge for CCD?
Yes, for the CCD.
CCD is operated in the minus 120 degrees Celsius. So just cooled silicon detector. And for the X-ray microcalorimeter is operated under the temperature of the 50 millikelvin. this is not using the superconductive, transition edge, but using the thermometer of the silicon detectors. Does it make sense?
I have a question. Can I ask a question?
Yes.
You mentioned that the cryogenic phase is 3 years.
Yes.
After that, there will be mechanical cooler. So for the mechanical cooler, what would be the temperature, and then what will be the energy resolution of the calorimeter with the mechanical cooler?
We expect to use the sensor with the same temperature, even with the mechanical coolers. So with the helium, liquid helium, we can use the mechanical cooler with lower power. So this may cause the very quiet condition for the sensor. So it is expected that the better energy resolution will be realized with the liquid helium, but without that, we require the same energy resolution with the mechanical cooler also.
Okay, thank you. This is wonderful. Thank you.
Okay, thanks. The questions. Any more questions?
Well, just to congratulate, because it's a new era, as you pointed out, for the microcalorimeter. And this gravitational redshift, all the way from white dwarf to active elastic nuclei to the large-scale structure of the universe, is really marvelous. Congratulations again.
Thank you very much.
Thanks. Thanks to the speaker. Okay, if not any questions, let's keep going to the last speaker of the session this morning, Professor Ruoyu Liu. He will talk about the first result of the NASA implication for extreme particle accelerators. Welcome.
Yes, thank you. Can you hear me?
Yes, but not the screen. Please tell your screen. Oh, no, it's okay.
It's okay? Okay.
Okay, yes.
And this is also the pointer. So you can see my pointer?
Yes. The read dot, yeah.
Okay, cool. Okay. Okay, so first of all, I would like to thank organizer for the invitation. I'm very glad to have this chance to talk about the first results of LASSO on behalf of the collaboration. This talk is about the ultra energy gamma ray sources detected by LASSO, as is shown the figure here. The ultra energy gamma ray source is defined as a source with emission higher than 100 TeV. Okay, so my talk will be there will be 3 parts. So first of all, I will introduce some research background on cosmic ray and ultra energy gamma rays. Then I will talk about the experiment, the Large High Altitude Air Shower Observatory. Then the third part will be the main part of this talk. I will talk about the discovery of 12 ultra energy gamma ray sources and their physical implications. Okay, then let's start with this figure for the spectrum of cosmic rays. So cosmic rays are charged particles from outer space. Their spectrum ranges from about 1 GeV to more than 10 to 11 GeV. Most of cosmic rays are protons, and they are arranged from some extreme processes or phenomena in the universe. So they are unique messengers for the extreme universe. Cosmic rays are ubiquitous in the universe. For example, in our galaxy, they constitute about 1/3 of the total energy density in the interstellar medium. So they also have very important feedback on galaxy and star formation, as well as the properties of interstellar medium. Therefore, to understand understanding the origin of cosmic rays will be very helpful to understand our universe. Currently, the consensus is that the cosmic rays above 10 to 18 EV is from extragalactic sources, while the cosmic ray below the spectrum break here, which is around 10 to 15 EV or 1 PeV, is from our galaxies. Although this cosmic ray is from nearby sources, relatively nearby sources, we still don't know exactly what are the sources and where are they. So the main difficulty of searching for sources of cosmic rays is because of the influence of the magnetic field. The magnetic field is universal in our galaxies, and cosmic rays are charged particles. So during the propagation of cosmic rays from their source to Earth, they will be deflected by the magnetic field. So if we look back into the along the arrival direction of cosmic ray, we won't see their real source. So this makes difficulty to pinpoint the cosmic sources. Then people come up with an idea of searching for the secondary gamma rays or neutrinos produced by cosmic rays if they produced inside their sources or nearby the sources. So if we can identify the signal of these secondaries from the spectrum of the source, then we can probe the source of cosmic ray, because these particles are neutral and they go straight line. Since LASSO is a gamma ray detector, so in this talk we will focus on gamma rays. To emit high energy gamma rays, these particles need to experience some interactions. For these gamma rays in our galaxies, for sources in our galaxy, there are main two procedures. One is the leptonic process, which is so-called proton-proton collision. In this case, a high-energy cosmic proton, when they arrive at some dense clouds, they have a high probability to interact with the atoms and produce pions. The neutron pions will decay into two gamma ray photons, and each of them takes about 10% of the parent proton's energy. So in the figure here, it shows the spectrum for a single proton-proton collision. The x-axis is the ratio between emitted gamma ray to the energy of a parent proton. We can see the spectrum peaks at 0.1. And the other procedure is so-called the inverse Compton scattering of electrons. So when electrons propagate in some low energy radiation field, they can scatter these low energy photons and pass their energy to this low energy photon and make them to ultra energy. For production of gamma ray above 100 TeV, the cosmic microwave background will be an important technical radiation field, because other radiation field of high energy will enter this so-called Klein-Shiner regime, and the cross section will become quite small. And so if we consider CMB as the target radiation field, then we can plot the relation between the upscattered photon energy and the electrons energy. We can see if we need to produce 100 TeV photon, then we need electron energy of like 300 or 400 TeV. And if the photon's energy goes to about 400 TeV, then we already need 1 PeV electron. So in this sense, the ultra energy gamma rays are important indicator for this PeV cosmic rays. So the technique to detect the high energy gamma rays is different from that of the low energy photons, such as in radio or in optical band. This is because high energy gamma rays, when they arrive at the Earth, they will be interacted with the atmosphere, and the initial gamma ray will be absorbed and generate electron and positron pairs. The electrons and positrons will further radiate new gamma rays via the Bremsstrahlung radiation process. And this process will repeat several cycles and generate more and more secondary particles. Also, the energy of these secondary particles will go down until it reaches the energy threshold for production of new electron and positron pairs. And LASSO can detect these electron positrons arrive at the ground. And based on their arrival time and the number of the events measured, then we can reconstruct the direction and the energy of the initial gamma rays. Now, on the other hand, cosmic ray can also initiate this air shower process because cosmic ray have a higher flux than gamma rays. Actually, they serve as a strong background or noise for the gamma ray detection. So the main difference in the gamma ray induced shower and the cosmic induced shower is that there are muons. There are muons in cosmic ray induced showers, and this will be used to discriminate the gamma ray induced shower from cosmically induced shower by LASSO. So here, this figure shows the layout of LASSO. So this blue circles and this red dots are the electron detectors and the muon detector, respectively. These two detectors, they compose the so-called kilometer square array, and they mainly work for gamma rays above 10 TeV. And in the central, this blue squares is the water Cherenkov telescope. So they mainly work for gamma rays below 10 TeV. And we can also see some black squares here. This represents the wide-field Cherenkov telescopes. They aim for detection of cosmic ray between 1 TeV to 1 eV. So the recent discovery of LASSO is mainly made by this electron detector and muon detector, or the KM2A. So here is the method to select gamma ray from cosmic ray background. So we define this parameter R, which is actually the number of muons to the number of electrons detected in one shower event. And the small number here is just to show this zero muon case. And in this figure, the x-axis is the reconstructed initial particle energy, and the y-axis is this ratio R. And the color is the probability of appearing at a certain energy and a certain ratio of a muon to electron by simulation. And we can see for gamma ray, if the shower is initiated by gamma ray, and most likely this ratio will be lower than 0.01 here. But if it is induced by a proton, then the ratio is most likely above 0.01. So for gamma ray photon above 100 TeV, then we can use this value of R as a simple cut to select gamma ray from the background. Below 100 TeV, this the proton-induced shower will also have a bigger chance to give rise to a very low ratio of R. So in this case, we need a stricter cut. And in this panel, we show example. So this this red curves is the expected gamma ray detection rate over the Crab Nebula, and this black curve shows the cosmic background detection rate from a window of a radius of 1 degree. So we can see the cosmic background detection rate is much higher than a Crab Nebula's rate. But if we apply for this muon cut to the cosmic background, then the rest of the cosmic background is quite low. It's below the Crab Nebula's detection rate, and this gives us a very good statistics. So in the bottom panel here, we compare the sensitivity of different instruments for very high energy and ultra energy gamma ray. We can see the LASSO's sensitivity curve is here. It has a very good sensitivity above 30 TeV. So the two reasons for this good performance is a large collection area and this strong background rejection power. Okay, then let's look into the LASSO's discovery. So this figure shows the sky map above 100 TeV viewed by LASSO. The white region is the sky outside the LASSO's field of view. And we can see there are some bright points here. These are the detected sources. They are all concentrated in this narrow band, which is the galactic plane. And here is the zoom, the figure zoomed into this region. Because we know the gamma ray, ultra energy gamma ray, will be absorbed by the cosmic microwave background and also the infrared background. So we do not expect to see ultra energy gamma ray sources from far away universe. We can see the plot here, which is the mean free path of gamma ray photon as a function of gamma ray energy, and above 10 to 14 eV here, which is 100 TeV, we can see the mean free path is about 3 or 4 megaparsecond. So that's why these sources are concentrated in the galactic plane, and we believe they are galactic sources. But if in the future we see somewhere here in high galactic latitude, we see some ultra energy gamma ray signals, then that would be very surprising and interesting. And here is the here is the table list the 12 ultra energy gamma ray sources detected by LASSO this time. We can see the here is the this column shows the maximum energy from these sources. We can see the highest energy 1.4 PeV photon is from the Cygnus region, and the second highest energy is from this one. This is the Crab Nebula. Now this highest energy is updated to 1.1 PeV. And in this table, we try to search for a counterpart at TeV or associated astrophysical objects to these sources. We can see most of the associated sources are pulsars or superlunar remnants, or also some with this young massive clusters. So these are also considered as the major candidates of cosmic accelerators in previous literature. So pulsars are this fast rotating and highly magnetized neutron stars. They have this fast rotator magnetic field. They drives they convert the rotation energy of the pulsar to the electromagnetic energy in form of Poynting flux. Then this Poynting flux accelerates electrons and positrons in the magnetosphere of the pulsar to ultra relativistic speed and form a strong pulsar wind. When this pulsar wind encounters the ambient medium, they will form a termination shock, and the electron positions in the pulsar wind will further be accelerated at the termination shock and give rise to broadband emission. For young pulsars, usually younger than 10,000 years, we will see the radiation is usually bright and compact because this accelerated electron positions are confined with a small region around the pulsar, such as the Crab Nebula. But if the pulsar the age is large, for example, larger than 10,000 kiloyears, these accelerated particles could escape from the pulsar nebula and they diffuse in the interstellar medium. And in this case, they will form extended and diffuse emission, such as this the Geminga halo as observed by Hawke. So pulsars are born in a supernova explosion. So such kind of supernova explosion is called supernova 1b or 1c or type 2 supernova explosion. They from the collapse of massive star when the nuclear fuel is exhausted. Another type of supernova explosion is type 1a, which arises from the accretion of white dwarf on its companion star. When the total mass of white dwarf exceeds the translational limit, it will turn into a supernova explosion. But no matter what types of the supernova explosion, they will drive very strong shocks to the ambient interstellar medium and form shocks. The initial speed of the shock can be faster than 10,000 kilometers per second, but it will get accelerated as it's swept up more and more particles from the interstellar medium. The particles will be accelerated in this shock front by when it cross between the upstream and downstream via this so-called the first order Fermi acceleration mechanism. And this acceleration ability of the supernova remnant shock is considered to be very reliable on the velocity of the shock. So people believe that the achievement of PeV particle acceleration may be only at the early phase of supernova remnant evolution. And another candidate is the young massive cluster. So this such kind of cluster contains a lot of O star and B star, which are massive star, maybe of mass more than 10 times the solar mass. So they have a very high temperature, high surface brightness temperature, more than 10 to let's see, more than 10,000 or even several tens thousand Kelvin. And the huge luminosity drives very strong stellar wind to ambient medium. the stellar wind speed can reach 1 to 2 kilometers per second, and it can also drive very strong shocks. And this figure shows the image in infrared for this cygnus cocoon region. And the highest photon energy, the 1.4 PeV photon, is from here, which is associated with one of the OB star association called Cygnus OB2. Is here. In the Cygnus OB2, the total number of O star and B star exceed 500, and the size of this Cygnus OB2 is about 10 parsecond. So we can calculate the average distance of the between each this O star and B star to be 2 parsecond. So they are quite close to each other, and the stellar wind can collide with each other and forming this colliding shock. So in this system, particle can be further accelerated to even higher energies. So then let's look at some detailed measurements by LASSO. So this two figures shows the image of LASSO for the Crab Nebula. This one is between 40 TeV to 400 TeV, and this is above 400 TeV. So Crab Nebula is a point source viewed by LASSO. The different size in these two images is due to the different PSF of the instrument. And we also measure the Crab Nebula spectrum from 0.5 TeV up to 1.1 PeV. And the local spectrum is about local spectrum slope is about 2.5 at 1 TeV, and then the spectrum goes suffers softenings, and when at 1 PeV it becomes 3.7. But we didn't see a clear cutoff here. So then we try to use this apply this the standard one zone model to fit the spectrum. In this model, the X-ray to GeV spectrum is explained by the synchrotron emission of electrons, and while the gamma emission above GeV arises from the inverse Compton radiation of electrons. So also in this one zone model, some model parameters such as the magnetic field and the radiation field and the electron spectrum is assumed to be spatially homogeneous throughout the nebula. In general, we can see the fitting is quite good. But if we look closely up at the spectrum above 60 TeV, as zoomed in this panel, we can see some deviation from the LASSO data, also from this log parabola fit shown with this blue curve. But currently, we cannot see such a deviation is significant. And the best fit parameters is shown here. The magnetic field is about 100 microgauss, and the maximum electron energy is about 2 PeV. So in this model, if we want to to explain this 1.1 PeV electron, then we reach very high energy electrons. So this energy is very high because the electron will suffer a huge loss in the magnetic field via the synchrotron radiation. So it implies an incredible particle accelerator operating inside the Crab Nebula. So this formula gives the acceleration rate of particle. So the epsilon here is the average electron field over the trajectory of particle trajectory. So if we because in astrophysical environment, the electric field is produced by the movement of magnetic field in most cases. So we can also rewrite this formula in terms of magnetic field, and then we introduce a parameter eta. Then this eta cannot be exceed 1 because the speed of this fluid cannot exceed the speed of light. And then this eta can be also considered as the acceleration efficiency. And we can also give this synchrotron energy loss rate by of electrons with this formula. And then if we equate this to formula, then we can get the requirement for this acceleration efficiency. Here we can say if the magnetic field is 100 microgauss, and to explain the 1.1 PeV photon, then we need this efficiency eta is larger than 15%. So this is a quite extreme acceleration efficiency. For comparison, this parameter in superpolar remnants many spectral remnants are found to be orders of 10 to -4. And also we can derive that the PeV electron production rate is more than 10 to 36 occurs per second. This is a very high value. Another interesting feature for the Crab nebula is the Crab flares. In Lasso's data, we didn't find any significant variability, temporal variability between TeV and PeV. But Crab flares are frequently discovered in MEV to GeV bands by Ageli and Fermi-Let. So these flares, they have very short time scale of a few days to a few weeks, and this implies the emitting region is quite compact, and also the magnetic field can reach the mini-Gauss. So in this case, actually we don't know how much of the flux in this MEV to GeV come from the flare states. Because apparently they are from a different radiation zone of the other wavelength emission, which is quasi-static. So if we exclude this emission, the MEV and the GeV emission from the SCD modeling, then we should have then for this let's say for this steady states for electron for this responsible for this steady state emission, they should have an early cutoff, for example, at this KeV energy. And then in this case, we also we can expect an early cutoff in the inverse Compton spectrum of electron. As such, then we need to introduce a second component account for the highest Lasso data here, either via a leptonic component or a hadronic component. But in any case, currently we cannot clearly see this second component exists because the statistics is not enough. Although we see here is we have some possible indication for the hardening of the spectrum at the highest energy end. Well, actually, Crab nebula is not the brightest source of the first detected 12 ultra energy gamma ray sources. The brightest three sources are here. This J2226 and J1908 and J1825. These three sources are famous galactic sources, which have already been extensively studied before. And the Lasso's spectrum for these sources are here, and the insets are the image above 25 TeV. There are some common features for these three sources. First, we can see the spectrum suffer a gradual softening with an increasing energy. But at the highest energy, we didn't see a clear cutoff of the spectrum. So in principle, the spectrum can continue to even higher energy. And probably if we wait for longer time, we will see the spectrum continues. And another common thing is that these are all extended sources. And in the source region, there are more than one associated source candidates. So for J2226, so we can see it's associated with the superpolar remnant G106, which is the middle-aged superpolar remnant, and also a possible nebula called Boomerang Nebula, which is powered by a very energetic pulsar J2229. Its spin-on power is about 5% of the Crab pulsar. In this figure, the green shows the radio emission of the superpolar remnant, and this different colors circles shows the gamma ray measurement. One interesting feature is that the centroid of the gamma ray emission is deviates from the location of the pulsar, and the red color here shows the distribution of a molecular cloud at this source distance, and the blue color represents the atomic cloud distribution. We can see the gamma ray position is a spatial coincident with this molecular cloud, which makes a hadronic arranging possible for this gamma ray emission. Which for this J1908, the situation is similar. We also have a superpolar remnant of middle age here, shown with this green dashed circle. And we also have two energetic pulsar, although it's not as powerful as this J229, but it's still we can still they are still energetic pulsars. One is inside the this superpolar remnant, and one is here. They can also contribute to the ultra energy gamma ray emission. And this color, this sky, this image shows the distribution of the molecular cloud. So in principle, hadronic emission can also arise from this region. And another source, J1825, is quite similar. So here we have two energetic pulsar of the spin-on power more than 10 to 36 ergs per second. One is here and one is here. This image shows the Lasso's image above 100 TeV. And this white contour shows the Hess emission for photon above 1 TeV. And this magenta circle shows the Fermi-Let's emission above 1 GeV. And this dark green contour shows the molecular cloud distribution. So in this situation, so we cannot tell exactly which source contributed to the measured ultra energy gamma rays by Lasso, or like how much fraction comes from this source and how much fraction comes from that source. We don't know. Actually, we even don't know exactly what is the origin of the the radiation mechanism of the ultra energy gamma rays, whether it's leptonic origin by PeV electrons or of hadronic origin by PeV protons, because both are possible. Another source I want to highlight is this G2108. So here is the Lasso's image in different bands. So this source, the special of this source is that it has no counterpart at the TeV, X-ray, or in radio band. So there's only one source in Fermi's 4FGL catalog, and after reanalyze of this source, we see an extended emission at the GV band, as shown in this blue circles here. And Lasso's emission is shown with this red circle here. And this in this plot, we also see in this region, we also see a molecular cloud appear here at a distance of 3 kiloparseconds. So from the spectral modeling, we try both a leptonic model and a leptonic model and a hadronic model. Because lack of the constraint in other wavelengths, so both of them are possible. So now the situation is that we know there are some ultra energy gamma ray sources there, and basically we can localize this source at a region with a size of 0.5 degree or less, but we don't know exactly which sources accelerate these high energy particles and whether the emitting particles are protons or electrons. So we need to use some other technique to help us to study the true origin. So first method is to utilize the multi-wavelength observation on the same region, especially the X-ray observation. This is because the X-ray observation actually probe the same electrons responsible for ultra energy gamma ray emission if they are of the leptonic origin. So in this case, if we use X-ray instrument observe some region, even if we don't find any significant emission, we can have a very crucial constraint on the electron component. And the second method is to use the neutrino observation. Neutrino observation, neutrino will be produced with this gamma rays in this proton-proton collision, because there are charged pions and the neutron pions will be produced simultaneously, and this charged pion will decay into neutrinos. And the expected neutrino flux and the gamma ray flux at the same energy is also comparable. So for some sources, if we can detect the neutrinos, it's not only serve as the smoke gun for the hadronic origin of the gamma rays. It will also tell us how much of the gamma ray emission can come from this hadronic process, and then the rest should come from the leptonic process. But currently, the ice cube, based on ice cube's effective area, we do not expect many significant neutrino detection for these ultra energy gamma ray sources. But next generation of neutrino telescopes should be able to detect the neutrino signals from the sources. And another method we can resort to is the observation of ultra energy gamma ray detectors with better angular resolution. So basically, there are two types of ultra energy gamma ray detectors. One is called air shower detector, such as LASO and HAWK, as shown in this figure. And another one is the Cherenkov telescope, such as HESS, Veritas, also CTA and MAGIC. They observe the Cherenkov light induced by this air shower generated by gamma rays. The advantage of the Cherenkov telescope is they have a very good angular resolution of 0.05 degree. For air shower detectors, the advantage is they have a large field of view and high duty cycle, but their angular resolution is worse than this type of telescopes. So if we can build an ultra energy gamma ray detector in this type, but with the comparable sensitivity of LASO, then we can have a better measurement of the morphology of these ultra energy gamma ray sources. So here is a simulation we made. So we assume here are two pulsar nebula and one superlunar remnant, and all these three sources emit gamma rays. So this is the intrinsic simulated image. And if we view this region via LASO, we cannot separate their contribution from each other. However, if we have a gamma ray detector of the same angular resolution of HESS, like 0.05 degree, then we can see there are this emission are composed of two sources here, and in this way we can see which source contribute how much flux of the ultra energy gamma rays, and then we can see we can know where these high energy particles are accelerated. Okay, so this is the main part of my talk. So to summarize, so LASO has discovered 12 ultra energy galactic sources with significance better than 7 sigma, and this opening the era of ultra energy gamma ray astronomy. And we find that the pulsar ring nebula, or pulsar halos, and superlunar remnants, and the young massive star clusters are most likely this PEV particle accelerator candidates for these gamma ray sources. And currently, except for Crab nebula, we don't know other sources, the astrophysical sources for other ultra energy gamma ray sources. And we need to utilize the multi-wavelength observation and the multi-messenger observation, or build a better angular resolution instrument for ultra energy gamma rays to unravel this the real source of galactic cosmic rays. Okay, that's all. Thank you very much.
Okay, thanks so much for your giving us these exciting talks. Any questions to Rory?
Well, you correctly pointed out with these 12 sources, this new era of ultra high energy cosmic rays. And also you have pointed out the relation with supernova remnant and the crab. But we are fascinated by this new ultra high energy cosmic ray following Agile, Fermi-LAT, and now going all the way to the PEV. As a theorist of black holes, I have a dream which I have not revealed yet, but I think there is something totally new in this second component of the crab. Something much very exciting. We are working, and maybe we will reveal some idea, but for the moment, let me express to you that indeed we are identifying a new era in this object, and very likely it's not only a neutron star, but there is something else which we are studying.
Yeah,
we will
thank you very much.
continue, but really it's a new frontier.
Yeah.
Okay, thanks the questions. Thanks the speaker again. Any more questions? Okay, if not, let's also thanks all the speakers of the session today. Bye-bye.
Okay, bye.
Just a brief announcement. The second block of the plenary session of today will continue at 9:30 Central European Time, which is in 40 minutes from now. We will have another session on the future missions. And after that, we will have a roundtable on the Galactic Center at 12 o'clock. Therefore, stay tuned. We just have a short break now. Thank you very much.
Thank you.